Okay, and we are, wait, are we live? No, not yet. All right, now we are live. So now we can get started. Maria's with Mr. Stevens. Okay, thank you. All right, so we are talking about applications of growth and decay today. We saw in the last class session how we can take a rate of change that is directly proportional to its original equation. So like in this case, dy over dt is the rate of change of y over time. And so when that rate of change is directly proportional to y, then we can go ahead and solve the equation, meaning find its original y equation, by using the theorem that says y is going to equal c times e to the k times t. And we proved that last class. We did all the integration for it. So because we've done that already, we can just invoke that theorem from now on. So whenever we have a phrase similar to this that says the rate of change of y is proportional to y, or some kind of similar phrasing, then we can go ahead and use that theorem, which means we basically don't have to do any integration. It's a lot of just kind of plugging in conditions, because that's what we did in this last problem here. They told us t is equal to y, t is equal to 0, y is equal to 2, and then t is equal to 2, y is equal to 4, and we use that to plug into the equation. So that's pretty much all we need in order to solve equations, is some kind of initial conditions there. And now what we're going to do is we're basically just going to apply this to different real world examples. This first one has to do with half-life. So just kind of a quick review in case you can't remember, or it's been a while since we talked about half-life. What this means is, for example, let's take this nobelium, right? If you have 10 grams of nobelium to begin with, it means that 23 seconds later, you should only have half of what you started with. So you would only have 5 grams of the nobelium. And then same thing like with radium. If you start with 10 grams of radium, that means after 1,620 years, you will have 5 grams, because that's half-life. So that means that it's decaying a lot slower than the nobelium would, right? Nobelium is like just a few seconds and it's already decayed halfway. Whereas radium, it takes over 1,000 years for it to decay that much. So it kind of goes to show the different rates of decay for each of these radioactive isotopes. And for our example here, it says that suppose that 10 grams of the plutonium isotope was released in the Chernobyl nuclear accident. We want to know how long will it take for the 10 grams to decay to 1 gram. And so I kind of skipped over this phrase up here. This is kind of important. Says we will work on the assumption that the rate of decay is proportional to the amount of the material. So rate of decay is proportional to the amount of material, obviously. So that is telling us that we can use the theorem. And so all we have to do is come up with our rate equation and then convert that to y. So we're going to say y represents the amount of the material. And so the change in y over time, so the rate of decay is what that dy over dt represents, is proportional to the amount of material. So is equal to k times y. So there's our rate of decay. And now we know that y, the equation for y, or the equation for the amount of material, is going to be c times e to the kt, because that is just using the theorem that we used last time. Okay. Any questions so far? Let me know if you have any. So now the actual question is asking, how long will it take for the 10 grams to decay to 1 gram? So how long means we need to know what is t equal to when y is equal to 1. Because remember, y represents the amount of material. So we want to know, what is t equal to when y is equal to 1? The 10 grams, how does that kind of fit in? Well, 10 grams is what we're starting with. So that means that if y is equal to 10, then t is equal to 0. That's an initial value for us. So we have two kind of sets of information here. One of them is incomplete, so we know that we can't use that one right away. This is the only one that has both t and y, which means that we can take both of those and plug them in to our equation here, y is equal to c times e to the kt, to hopefully be able to solve for c and or k. Those are the two that we need to solve for in order to get a particular solution here. So let's go ahead and just plug that in. Y is equal to 10 and t is equal to 0. So when I plug that in, k times 0 is 0, e to the 0 is 1, so we're left with c is equal to 10. C is always going to represent your initial value. So it makes sense that C is equal to 10 because at the start, what we see here, when T is equal to 0, we have 10 grams. So C equaling to 10 should make sense. And then once we got that, we can plug it in to the equation. So that's our new equation so far. Let me make that K better. All right, but that's still not enough for us because we can't plug in this y value and then get a t value as an output because we don't know what k is equal to. So we need another set of information in order for us to solve this. So what do? We go back to this chart here, and it says that plutonium has a half-life of 24,360. So that means when T is equal to 360, what is our Y going to equal? Well, since it's the half-life, and we are starting with 10 grams, after 24,360 years, we should have 5 grams. We have half of what we started with. So that's just, with this particular problem, because we're starting with 10 grams. Let's say maybe instead you started with 20 grams, then your Y would have to equal 10. Just depends on what you're starting with. So,
Miss Mark.
Yes?
Just a quick question. What did you say K represented again?
So K represents like your rate of decay. So if you have, because y is equal to c times e to the kt, right? So k is kind of like, if it's positive, it's telling you it's going to be a rate of growth. And then if it is negative, that means it's going to be decaying, right? So it's going to be negative. Since it's an exponential function. So we need to solve for that k. But now that we have this information, we can go ahead and plug it in to this one. So we have 5 is equal to 10 times e to the k times 24,360. And then from here we can solve for k. We just need to divide by 10, so that's going to be 1/2. And then to get rid of e, we'll take the ln of both sides. So we have ln of 1/2 is equal to ln e to the k times 4,360. So now ln and e will cancel out. And we're left with 24,360 times k. Divide by the 24,000. K is equal to ln of 1/2 divided by 24,360. From here, we can go ahead and plug it into the calculators to get a decimal value, but you can also just use this as it is and plug it into the equation. It's actually going to give you a more exact value, because when you get the decimal, you would have to round, and so then it wouldn't be an exact value. But that's why we're just going to go ahead and take this k and plug it right into the equation. Even though it looks kind of messy because it's kind of big, you actually technically could simplify this further, because ln of 1/2, if you use your log properties, would be ln 1 minus ln of 2. But like I said, we're going to just end up plugging everything into the calculator anyway. So I'm just going to go ahead and plug that whole thing in. So our new equation, I'll do it in a different color. Y is equal to 10 times e to the ln 1/2 divided by 24,360 times t. Okay, so there's our equation. If you graph it out, it would show you the decay of plutonium. And so, but what we want to know is at what time is there going to be only 1 gram of material. So I'm going to plug that in for y, and then we can go ahead and solve for t. So kind of the same process that we used to solve for k. We're going to have to first divide by 10. So we get 1/10 is equal to e to the ln 1/2, 24,360 times t. We need to take the ln of both sides. So we have ln 110. Let me just write it here so we know those are going to cancel. And then we're just left with ln of 1/2 divided by 24,360 times t. And then the last step to solve for t, I'm just going to multiply by the reciprocal of this fraction. So t is to equal 24,360 times ln of 110 divided by ln of 1/2. So there's t, and then you can just plug that into your calculator, and that is going to be approximately, oh, I ran out of room here. Write it on the other side. Approximately 80,922 years. Okay, so sometimes mistakes happen, and so what we want to do is kind of think back to the problem. And if you have your calculator, you can kind of check it as well with this equation. You graph the equation and then kind of take a look at what it looks like. But if our half-life is 24,360, then it would make sense that in order for us to have just 1 gram, it should take longer than 24,360. And the reason I'm saying that is because actually, when I wrote this, I put a point instead of a comma. I put 80.922 just by accident. And then I was like, wait a minute, let me think this through. This doesn't make sense. So that's kind of just something to keep in mind too, is take a look at the information you're given, look at it closely so you can kind of double check your work as you go. So that is our answer here, 80,922 approximately. Let me know if you have any questions before we move on. Or even if something comes up, let me know, I can come back to it. So let's take a look at the next problem. So we have a experimental population of fruit flies, and it increases according to the law of exponential growth. So this is a new phrase that we haven't necessarily seen, but it's similar to our phrasing here, where it says the rate of decay is proportional to the amount of material. So it's saying the same thing, that this property applies. So we can go ahead and use that theorem the same way that we used it in example 3. It says there were 100 flies after the second day of the experiment and 300 flies after the 4th day. Approximately how many flies were in the original population? Round to the nearest fly. So we know we can start out with dy over dt is equal to k times y, where y represents the number of flies. So it's the rate of change of the number of flies over time, and it's directly proportional to the number of flies. And now we know y is equal to c times e to the k times t. And it's increasing is what they told us here, right? So what we should keep in mind is that this k is going to have to be a positive number, because obviously if it's an increasing function, it's growing, right? So we need it to be positive. Whereas in this last problem that we did, even though we didn't plug it into our calculators to check, k is negative because it's a decay. Actually, a really quick check I just noticed here. ln of 1 is equal to 0, right? So this actually gives us just negative ln of 2 over 24,360. So you can already see and check that that is actually negative. Okay, back to this problem. So we know k should be positive, but we need to figure out what information we can use to plug in and solve. So it says that there's 100 flies after the second day. So it means when t is equal to 2, y is equal to 100. And then it says 300 flies after the 4th day. Oops. All right, so they didn't give us any initial value, so that means we don't know right away what c is equal to. We're going to have to do a little bit of extra solving in order to do that. So we can start with either one of those two points. Doesn't really matter because we don't have 0. So let's just start with t equal to 2 and plug it in and see what happens. So when we do that, you can see here that we can't solve for either c or k. But what we'll do is we'll solve for c. There's just going to be a k in the equation that we're going to have to figure out after this. So c is going to equal 100 divided by e to the 2k. So I just isolated the c. And what we can do is we can do substitution here. So this c, I'm going to plug it in. So we get y is equal to 100 divided by e to the 2k times e to the k t. So at least now we've gotten rid of c, or at least now c is a function of k, so that k is our only variable that we need to solve for. So we can try and simplify this. Oh, thank you.
You're welcome.
I'm in class now.
Oh, sorry.
My little sister just brought me coffee, so now I'm an instant math teacher. Yeah, she's got the hiccup. Look at that. Instantly Miss Martin now. And it matches everything too. Okay, so yes, we will derive. Through all of this mayhem, we will derive. All right, so from here we can plug in the next set of information to try to solve for k, which is t equal to 4 and y equal to 300. Do a different color. Let's actually kind of rewrite this too, so that things can look kind of neater, because we have 100 divided by e to the 2k, and then that's being multiplied by e to the kt. So this is technically, if I wanted to rewrite it a little, e to the kt divided by e to the 2k. Which we can also simplify, because when you're dividing two things with the same base, it's the same thing as not multiplying, subtracting. So let's actually plug in the value here, and then we can do that. So, because I forgot to plug in t. So this becomes 4k. So I plugged in this t value and this y value, 4 and 300. And from here, then we can just easily subtract, because we have the same base e. So it's just going to be 4k minus 2k, which is 2k. And now that looks a lot neater and easier. So we divide by 100. 3 is equal to e to the 2k. Take ln of both sides. So we get ln of 3 is equal to 2k. And k is equal to ln of 3 divided by 2. So that we can take and plug into our equation again. So we're starting with this. So we can plug that into k, and actually now we can solve for c because we know what k is. So let's take that value. So this is a lot of just kind of plugging in, simplifying, plugging in, simplifying, a lot of substitution, right? So I'm sorry it got kind of messy, but if you kind of follow the arrows through, right, we kind of started here, we went here to then go here, and then from here we're gonna jump over to solve for C, and then we'll get our final. I'll kind of continue it over here. So we have 100 divided by e to the 2 times ln of 3 over 2. So I'm plugging in the k that we just solved for here. And the 2's will cancel, leaving me with 100 divided by e to the ln of 3, and e and ln cancels. So I'm left with c is equal to 100 divided by 3. So that's our initial value too. Okay, so c is equal to 100 divided by 3. K is equal to ln 3 over 2. We can now take both of those, plug them in to this equation, and now we have an equation that we can plug anything into. So we have y is equal to 100 over 3 times e to the ln of 3 over 2 times t. And the question was asking us to find out approximately how many flies were in the original population. Technically, we already found that because remember I said C is your initial value, but we can just prove it because that would mean we need to know when t is equal to 0, what is y equal to? So we can plug in 0 for t here. Which is just going to give us e to the 0, which is just 1. And so we're left with y is equal to 100 divided by 3, or approximately 33 flies. Oops. So that's how many we started with. Questions? Let me know. I hate those pesky little fruit flies. Start with 33, the next day you have 100. That's crazy. Okay. Ready for, is this our last one that we're doing? Yeah, this is our last one that we're doing for today. What time did we get out? 10:40. Okay, cool. All right. 4 months after it stops advertising, a manufacturing company notices that its sales have dropped from 100,000 units per month to 80,000 units per month. If the sales follow an exponential pattern of decline, what will they be to the nearest unit after another 2 months? So that phrase there, it's following the exponential pattern of decline, tells us we can use that theorem. So we have dy over dt is equal to k times y. And what does y represent? The number of units. So it's important to always, when you write an equation, you want to make sure you understand what are all the parts, right? So dy stands for the rate of change of y, so the rate of change of the number of units, dt is over time, is equal to k times y. So that means it's directly proportional to the number of units. All right, and that means we can use our theorem to know that y is equal to c times e to the kt. Now let's see, what did they tell us? It says 4 months after it stops advertising, a manufacturing company notices that its sales have dropped from 100,000 units per month to 80,000 units per month. So that means that when they started, when t is equal to 0, y is equal to 100,000 units. So they're actually telling us the initial value, and then also 4 months later, we are at 80,000. So now we can take this initial value. We know now C is equal to 100,000. We can show the work to prove it. All we have to do is plug in Y, 100,000, and plug in T is 0, and then we get C is equal to 100,000. So there's your initial value, and we can go ahead and plug that in to our equation. So y is equal to 100,000 e to the kt. Now we are going to use the next piece of information. Gosh, I can't zoom out here. Maybe I should do this. So t is equal to 4, y is equal to 80,000. We can plug that in here and solve for k. All right, so divide by 100,000, we get 80 over 100, that's going to be 4/5 e to the 4k. ln of both sides. Notice we're starting with the same equation, so solving is going to become the same thing for the most part. So we have ln of 4/5 is equal to 4 times k. Divide by 4, so k is equal to ln 4/5 divided by 4. There's the k value. We'll take that and plug it in. Let's do a different color. Let's do pink. So our equation is y equal to 100,000 e to the ln of 4/5 divided by 4 times t. Now, what did they want us to figure out? What will they be to the nearest unit after another 2 months? So this is a tricky question. They're trying to trick you into writing t is equal to 2 because, right, after another 2 months, that is wrong because we're already 4 months in, right? We start at 0 and then it says 4 months after we're at 80,000. So we want to know after another 2 months, how many units are we going to be? So that means t is equal to 6. So we're trying to figure out what y is equal to when t is 6. We're going to go ahead and just plug in t, and then we can solve for y. Okay. ln 4/5 divided by 4 times, not t, 6. Because t is equal to 6. And from here, we just need to plug it into the calculator because y is already isolated. That's what you're trying to solve for. And then you just plug it into your calculator. And we have y is approximately 71,554 units. Okay. Any questions?
That number is units after 6 months, right?
Yes.
Okay.
Any other questions? Okay. So the reason that I am wearing this t-shirt today, instant math teacher. It's because I wore it in a video that I'm about to play for you all. It's a little bit old, so you're going to see I look a lot different, but it's still 100% relevant. It involves Newton's law of cooling, which you see at the bottom of your notes there. So go ahead and enjoy the show. Let me share my other screen so you guys can watch. I don't have excellent editing skills like our friend Ned does, but I tried. This was for a project in my master's class.
Ed.
So you guys enjoy the show. Let me make this full screen. Do you all? Wait, I want to make sure. Can you all see?
Yes.
Okay, and you can hear? Yes. Okay, cool. Here we go. Here we see Miss Martin working long, hard hours trying to get all of her grading done for her wonderful students. All of that hard work is starting to make her a little bit sleepy. When she wakes up from her nap, there's only one thing on her mind. Coffee. Miss Martin can't drink coffee unless it's in her I ate some pie and it was delicious mug. Uh-oh, she got burnt. Have you ever wondered how long you should have waited before taking a first sip out of your coffee instead of getting burned like Miss Martin just did? Well, now Miss Martin is going to help us figure this out using good old calculus.
So this is the perfect opportunity for us to use Newton's law of cooling. So Newton's law of cooling says the rate of change of an object is proportional to the difference between its own temperature and its surrounding temperature. So let's see if we can write an equation out of this definition here. We see the first phrase says the rate of change of an object. So how do we write rate of change? Well, rate of change is the same thing as a derivative. So we're going to write dt over dt. So how did I come up with that? Well, we see at the top here, this capital T stands for temperature. So this is the change in temperature over the change in time. So the rate of change of an object is dt over dt. Then we see the word is. So the rate of change is, whenever we see that, we want to write equals. So it is proportional to the difference. So when we see proportional, that just means we are multiplying by a constant. So I'm going to use just the letter K as a constant. And it's proportional to the difference. So when we see difference, we know it's going to have to be subtraction between its own temperature and its surrounding temperature. So I'm going to use capital T to represent temperature, the object's temperature, just like we used capital T here to represent the change in the object's temperature. So this is the temperature, change in temperature, and then we're going to subtract the surrounding temperature. So I'm going to use capital T again with a little s there to represent surrounding temperature. So this is the equation that represents Newton's law of cooling. So now we have our equation for the rate of change based off of Newton's law of cooling. I did make sure to put a negative here because it is the law of cooling. So that means that we want to have a rate of change that is negative because it's going to be decreasing. And so what we have here is called a differential equation because it really is a derivative of the temperature. In order for us to solve for the original equation of this temperature, we're going to need to integrate this because integration is the opposite of derivatives. If we have a derivative here, we're going to have to integrate it to get the original solution and get the general solution is what we call it. General solution is what we're looking for. Okay, so what we need to do is use the strategy of separation of variables. We see here we have the variable for T and we have capital T for temperature, and we have the variable for lowercase t for the time. So what I want to do is move over here where I see this capital T. I'm going to move this over by dividing to the other side to get it together with this capital T that I see here. And I'm going to move this d over t over to the right side by multiplying it over so that we can then separate these two variables. So dividing by t minus t sub s, we're going to get 1 over t minus t sub s on the left side times dt, because this dt is not moving. The negative k is also going to be staying, but we're multiplying by dt to the other side, so we have negative k times dt. Now that we've separated the variables, we can actually integrate. So we'll integrate both sides. This right here reminds me of the integral of 1 over u, so it's a u substitution. The integral of 1 over u is equal to ln absolute value of u. So I can go over here and I know that this integral is going to be ln absolute value of whatever's down here, which is t minus t sub s. The dt goes away because we've integrated, so the integral goes away, the dt goes away. Normally we add the constant, but since we're still going to be integrating on that side, we'll add the constant to the other side. The integral of any constant is the constant times the variable here. So the variable is t, so this integral is going to be negative k times t, and now we're going to go ahead and add our constant there. We want to be able to solve for t, so first of all we want to think about these absolute values here. This t represents the temperature of my coffee, and this t sub s represents the temperature of the room. So I know that my coffee is hotter than the room, so if we have the temperature of my coffee minus the room temperature, it's still going to be positive. So we can go ahead and get rid of those absolute values because we know that they're always going to be positive, so we don't need them there. And we want to solve for t, so to get rid of ln, we're going to take e of both sides. So now this whole thing becomes our exponent to e, and e is our base. And same thing here, except e now cancels ln, so we're left with t minus t sub s. On this side, e to the negative kt plus c is the same thing as e to the negative kt times e to the c. E to the c is just going to be a constant, so we can replace that with a c. Really, this just becomes c times e to the negative kt. The last thing we want to do to be able to solve for t is add this t sub s to the other side. So t equals c times e to the negative kt plus t sub s. Alright, so now that we have the equation for temperature, we can start to kind of look at its different parts and see how it fits in with the problem. So of course, capital T stands for temperature of my coffee. C is a constant, which we got from the integral, and K is another constant, so we're going to have to solve for these constants in a bit. And then we have lowercase t, which stands for time, and uppercase T sub s stands for the temperature of the surrounding area. So in this case, the temperature of my house, which at this point is 74 degrees, or at least at the time where I made my coffee. So here we see a chart where at time equals 0, I checked the temperature and it was 160 degrees. And at that point I took a sip and of course it burned my tongue. So I want to figure out how long it'll take for the temperature to go down to about 135 degrees. I saw online that 140 degrees is about the average temperature for a drink, but after that burn, I want to make sure that I don't burn myself again, so I want to take a sip once it goes down to 135 degrees Fahrenheit. So after 2 minutes, I saw that the temperature went down just 5 degrees Fahrenheit to 155 degrees. So instead of waiting it out, I decided let's use Newton's law and see what we can come up with the time will be for me to finally take my next sip without burning myself. So what we want to do is start out with this initial information where t equals 0, lowercase t equals 0, and uppercase t equals 160 degrees. So we have our uppercase t and our lowercase t there, which we will plug in. So 160 equals c e to the negative k times 0, and we're also going to plug in 74 degrees there. Anything times 0 is going to give us 0. E to the 0 power is just going to be 1. 1 times c is just going to give us c. So to solve for c, which we said we needed to figure out that constant, we're just going to subtract 74 to the other side. So 160 minus 74 gives us 86. So we now know that this constant is 86, and we can plug it into our general solution here. So our new equation is t equals 86 e to the negative kt plus 74. We're going to keep that plugged in there. The next step is we need to figure out what this k constant is. So we'll use the next information. If we plug in 0 again, it's going to make this k go away because 0 times k is going to become 0. So we don't want to use this information anymore. We're going to move on to plug in 2 and 155 degrees, and then we'll solve for k that way. And we'll find out that k is equal to ln of 155 minus 74, all divided by 86, and all divided by -2. So this would approximately be 0.0299, and that will be our value for k, which we will then plug in here. So as of now, we have T of S, which is 74 degrees. We have figured out what K is, and we have also figured out what our C is. So let's write out what our equation now looks like. We have T equals 86 e to the negative 0.0299, that was our K, times T plus 74. This is now our equation for temperature, so we can plug in any temperature and solve for T, which is time, or we could plug in any time and figure out what the temperature will be at that time. My goal is to figure out how long will it take for me to finally take a sip when the coffee reaches 135 degrees. So I'm going to take 135 degrees, plug that in for my T, and I will need to solve for that T value there. Once I finally solve for this T, we will find out that T is equal to approximately 11.46 minutes. So that tells me that from the time that I made my coffee, I should wait about 11 minutes before I take my sip, because otherwise I might end up burned.
All right, so that is our video on Newton's law of cooling. Hope you all enjoyed that little presentation there. Let me stop sharing this screen here. Thank you, I appreciate it. So that means that on Friday, we're going to do another example together on Newton's law of cooling, just to kind of make sure we get the gist of it. And then we're going to do one more topic, and then we're pretty much done with calculus for this year. At least the calculus that we need for the AP exam, because remember that we are not going to be having to go over the last unit of calculus for the AP exam. We're still going to touch on it. We're still going to kind of talk about it. But you know, we want to focus on making sure we're prepared for the exam, which is in a few weeks. So yeah, we're kind of already at that point from here on out. So just one more topic that we'll cover tomorrow, and then we're ready to rock and roll with review. So let me know if you have any questions, but that is the end of class today. I hope you all have a great rest of your day.
Thank you, Ms. Martin. Bye.
You're welcome. Bye.
Thank you, Miss Martin.
You're welcome.
Thank
Bye.
you.
See ya.
Miss Martin, your editing is better than Ned's.
Thanks. I tried.
That's true.
I still need more practice. Goodbye. Have a great day, everyone.
Miss Martin,
Yes.
isn't it true that this year we got the most days off for the Bosco film?
Is it true? You didn't get 5 days though, did you?
Well, we got the whole school year.